Let me paint you a picture. It's Mother's Day weekend, May 2024. You're scrolling through social media and suddenly your feed explodes with photos of brilliant red and green auroras. Except they're not from Alaska or Norway. They're from Florida, Puerto Rico, Mexico, places that should never see the northern lights.
And that's when people started asking the very reasonable question, what the hell is happening?
Exactly, because while everyone was outside taking Instagram photos, satellites were getting fried, power grids were straining, and GPS systems were going haywire. All because a sunspot the size of 15 Earths decided to have a temper tantrum.
AR3664, the most active sunspot region of solar cycle 25 and arguably one of the most dramatic solar performers we've seen in over 2 decades.
It launched multiple coronal mass ejections, billion-ton clouds of plasma, traveling at speeds up to 3 million miles per hour toward Earth. That's fast enough to cross the 93 million-mile gap in less than a day and a half.
And when those plasma clouds hit our magnetic field, we got the first G5 class geomagnetic storm since 2003. Welcome to solar storm AR3664, the 3 million mile per hour blast that painted Earth in fire. I'm Dr. Elena Vasquez.
And I'm Marcus Chen. Today we're diving into the solar storm that made headlines worldwide, why it was both beautiful and terrifying, and why this might be a preview of what's coming as we approach solar maximum.
Spoiler alert, the sun is waking up and it's not particularly gentle about it.
So grab your eclipse glasses and let's talk about the weekend the sun reminded us who's really in charge. All right, Elena, set the scene for me. What happened on Mother's Day weekend 2024?
So on May 10th through 12th, 2024, Earth experienced the most intense geomagnetic storm in over 20 years. NOAA's Space Weather Prediction Center issued a G5 class storm warning, the first since the Halloween storms of 2003.
And G5 means?
It's the top of the scale. Think of geomagnetic storms like hurricanes. G1 is a tropical storm, G3 is a strong hurricane, and G5 is a Category 5 monster. It means extreme geomagnetic storming with widespread effects on power systems, satellites, and communications.
So this wasn't just pretty lights in the sky.
Oh, it was definitely pretty lights, but those lights were the visible symptom of our planet's magnetic field getting absolutely pummeled by billions of tons of solar plasma traveling at millions of miles per hour.
Let's back up. What caused all this?
A sunspot region called AR3664. Active region 3664 was a massive cluster of sunspots that appeared on the sun in early May. And when I say massive, I mean you could see it with your naked eye if you wore eclipse glasses.
Wait, you could see this thing without a telescope?
Yes! It was about 16 times the diameter of Earth. That's roughly 125,000 miles across. People were posting pictures on social media of this dark blob on the sun's face that they could see through their solar eclipse glasses from April.
That's both cool and deeply unsettling.
Welcome to space weather. So, starting on May 8th, AR3664 began unleashing a series of powerful solar flares, X-class flares, which are the most intense category.
How many flares are we talking?
Multiple X-class flares over several days. An X 1.0, followed by an X 2.25, an X 1.12, then an X 3.98, and culminating with an X 5.8 on May 11th. But here's the kicker. Each of these flares was associated with a coronal mass ejection.
Okay, so we've got solar flares and CMEs. For people who slept through astronomy class, what's the difference?
Great question. A solar flare is essentially a massive explosion of electromagnetic radiation. Light, X-rays, radio waves. It travels at the speed of light, so it hits Earth in about 8 minutes. It's pure energy, no mass.
So it's fast, but relatively harmless.
To us on the surface, yes, because our atmosphere absorbs most of it. but it can disrupt radio communications and GPS signals. The real threat comes from the CMEs.
The coronal mass ejections.
Right. A CME is when the sun literally ejects a chunk of its atmosphere, billions of tons of plasma, which is superheated gas made of charged particles, mostly protons and electrons. This material is embedded with powerful magnetic fields.
And this is the stuff traveling at 3 million miles per hour.
Some CMEs can reach those speeds, yes. The fastest ones can make the journey from sun to Earth in 15 to 18 hours. Slower ones take a few days. The average is about 3 to 4 days.
So AR3664 threw multiple billion-ton plasma bombs at Earth?
At least 7 distinct CMEs between May 8th and May 11th. And here's where it gets interesting. Some of them were catching up with each other in space, creating these merged, extra powerful structures.
Like cars piling up on a highway.
Actually, that's not a bad analogy. When faster CMEs overtake slower ones, they can merge and create these massive, complex structures with even stronger magnetic fields. That's partly why this storm was so intense.
Okay, so walk me through the timeline. When did things start getting wild?
The first CME reached Earth on Friday, May 10th at 12:37 p.m. Eastern Time. NOAA's Deep Space Climate Observatory, or DSCOVR, sitting at the L1 Lagrange point about 1 million miles from Earth, detected the shock wave about an hour before impact.
So we had warning?
About an hour's warning that it had arrived at the L1 point, yes. But NOAA had been tracking these CMEs for days. They issued the initial geomagnetic storm watch on May 8th, upgraded it to a warning on May 9th, and by May 10th, they were holding emergency press conferences.
Emergency press conferences about space weather. That's how you know it's serious.
Absolutely. This was unprecedented in recent memory. NOAA was calling power companies, satellite operators, airlines, anyone whose operations could be affected. Because once that first CME hit, conditions escalated rapidly.
What happened?
By Friday evening, we were already seeing auroras as far south as the mid-latitude United States, places like Iowa, Arkansas, even northern parts of Texas. But that was just the warm-up. The peak came overnight on May 10th into May 11th.
When the pictures started flooding social media.
Exactly. Auroras were visible from Puerto Rico, latitude 18 degrees north. From Mexico, from South Africa in the southern hemisphere. The KP index, which measures geomagnetic activity, hit 9, the maximum.
And the KP index is?
It's a scale from 0 to 9 measuring disturbances in Earth's magnetic field. Under normal conditions, it's around 2 or 3. You need a KP of 7 or higher for auroras to be visible at mid-latitudes. A KP of 9 means the entire planet's magnetic field is convulsing.
That's a technical term, convulsing.
It's the term I use when our protective magnetic bubble is being absolutely hammered by 1 billion tons of charged particles traveling at 3 million miles per hour. The more technical term is severe magnetic field disturbance.
So the magnetic field is shaking, and that creates the auroras.
Essentially, yes. When the CME slams into our magnetosphere, some of those charged particles get funneled down toward the poles along magnetic field lines. When they hit our upper atmosphere at altitudes between 60 and 200 miles, they collide with oxygen and nitrogen atoms, exciting them to higher energy states.
And when those atoms relax back to their ground state,
They emit light. Green light from oxygen at lower altitudes, red from oxygen at higher altitudes, and purple or blue from nitrogen. The colors depend on the altitude and which gas is being excited.
Okay, but here's what I want to know. Why was this storm so much more intense than usual? We have solar storms all the time, right?
We do, but several factors made AR3664 special. First, the sheer number and intensity of the CMEs. 7 major eruptions in a few days, some merging together. Second, the magnetic field orientation.
You're going to have to explain that one.
Sure. So CMEs carry magnetic fields with them. It's called the interplanetary magnetic field. The orientation of that field determines how strongly it couples with Earth's magnetic field. If the IMF points south, it can actually open up our magnetic field and allow solar material to pour in.
Like picking a lock.
Exactly. And during this storm, we had sustained periods where the IMF was pointing south at nearly 50 nanoteslas. That's incredibly strong. Our magnetic field basically couldn't keep the solar material out.
So the sun found the key to our defenses.
In a sense, yes. The solar wind speed was also elevated, 750 to 950 kilometers per second, which is well above the normal 400 to 500. And the density was high too. All these factors combined to create what scientists call a perfect storm.
How does this compare to historical storms? I keep hearing about the Carrington Event.
Good question. The Carrington Event in September 1859 remains the gold standard for extreme space weather. That storm had an estimated DST index, a measure of magnetic field strength, of around negative 900 nanoteslas, possibly as low as negative 1,750 nanoteslas.
And May 2024?
Peaked at around negative 412 to 518 nanoteslas, depending on which measurements you trust. So significantly weaker than Carrington, but still the strongest since March 1989.
The storm that knocked out power in Quebec.
Exactly. That one hit negative 589 nanoteslas and caused a 9-hour blackout affecting millions of people. The May 2024 storm was in that same ballpark.
So we dodged a bullet.
More like we got grazed by a bullet. If the magnetic field orientation had been more favorable or unfavorable, depending on your perspective, or if the CMEs had been even faster, we could have seen Carrington-level impacts.
Which would mean
Widespread power grid failures, satellite losses, communication disruptions lasting days or weeks. We'll get into the what-if scenarios later, but for now, let's talk about what actually happened on the ground.
All right, so we've established that May 2024 was a big deal. But I want to know, beyond the pretty lights, what actually happened? Did anything break?
The good news is that we didn't see catastrophic failures, but we came closer than most people realize.
That sounds ominous.
Let's start with power grids. During a geomagnetic storm, when Earth's magnetic field fluctuates, it induces electric currents in long conductors, like power lines and pipelines. These are called geomagnetically induced currents, or GICs.
And those currents can damage equipment?
They can. GICs flow into high-voltage transformers, which aren't designed to handle DC current. This can cause transformers to overheat, saturate, and in extreme cases, permanently fail. And here's the scary part. These transformers are expensive, custom-built, and take months or years to replace.
So if a major transformer blows...
You're looking at extended blackouts. In Canada, BC Hydro and Hydro-Quebec were monitoring conditions closely throughout the weekend. They learned from 1989 when Hydro-Quebec's grid collapsed.
Did they lose power this time?
No, and that's a testament to improved infrastructure and forecasting. They knew the storm was coming, they took precautions, and the grid held. But NOAA did report power grid irregularities in the United States.
What kind of irregularities?
Fluctuations in voltage, unexpected currents showing up in neutral lines, transformers running hotter than usual. Nothing that caused outages, but operators were definitely sweating.
And if the storm had been just a bit stronger?
Then we might have seen localized blackouts, possibly cascading failures in vulnerable parts of the grid. The fact that we didn't is partly good design and partly good luck.
Okay. What about satellites? Those got hit, right?
Oh, satellites had a rough weekend. Let's start with Starlink. SpaceX's constellation of low Earth orbit satellites experienced degraded service during the storm, but remained operational.
What does degraded service mean?
Increased atmospheric drag from the storm caused their orbits to decay faster than expected. The satellites had to perform emergency maneuvers to maintain altitude. In fact, nearly half of all active satellites in low Earth orbit maneuvered during the storm.
Half of all satellites? That's insane.
It's unprecedented. When a geomagnetic storm hits, it heats and expands Earth's upper atmosphere, the thermosphere. That creates more drag on satellites, pulling them toward Earth.
So they have to burn a fuel to climb back up?
Exactly. And if they don't have enough fuel, or if the storm is severe enough, they can be pulled into lower orbits and eventually burn up in the atmosphere. During the 1989 storm, NORAD temporarily lost track of many satellites.
Did we lose any satellites in May 2024?
Not that we know of publicly, but ESA's Gaia spacecraft, the one that's been mapping the Milky Way, reported electrical problems during the storm. That's a spacecraft sitting 1 million miles away in a stable orbit, and it still got zapped.
What kind of electrical problems?
The increased radiation environment can cause what's called single event upsets. Basically, a high-energy particle hits a computer chip and flips a bit from 0 to 1, or vice versa. If that happens in a critical system, it can cause anything from minor glitches to complete system failures.
And there's no way to prevent that?
Satellite designers build in redundancy and radiation shielding, but you can never eliminate the risk entirely. During severe storms, operators often put satellites into safe mode, shutting down non-essential systems and orienting solar panels to minimize exposure.
Which means those satellites can't do their jobs.
Right. During the storm, some Earth observation satellites, GPS satellites, and communication satellites all had to take protective measures. The economic impact of that is hard to calculate, but we're talking about disruptions to everything from shipping logistics to precision agriculture.
And what about GPS? I remember hearing that was affected.
GPS took a hit. The storm ionized Earth's upper atmosphere, which interferes with radio signals passing through. GPS signals travel from satellites to receivers on the ground. And when the ionosphere gets charged up, those signals get delayed and distorted.
So your phone's map app was lying to you?
More like your phone's map app was confused. Accuracy probably degraded from the usual 5 to 10 meters to potentially 50 to 100 meters or more. For most people using turn-by-turn navigation, that's not catastrophic. But for precision applications, surveying, autonomous vehicles, precision agriculture, that's a real problem.
And airlines?
Airlines had to deal with 2 issues. First, GPS degradation affected navigation, especially for aircraft at high latitudes. Second, high-frequency radio communications were disrupted.
So planes couldn't talk to air traffic control.
HF radio was unreliable, yes. The X-rays from solar flares ionize the D layer of the ionosphere, which absorbs HF radio waves. During the peak of the storm, we had R3 level radio blackouts. That's strong, on a scale from R1 to R5.
What does that mean, practically?
Flights over the poles or across the Atlantic and Pacific had to use alternative communication methods. Some flights were rerouted to avoid high-latitude regions where conditions were worse. The FAA and international aviation authorities issued advisories.
So if you were flying that weekend, you might not even have known your flight was affected by a solar storm?
Exactly. The aviation industry handled it professionally, but behind the scenes, there was a lot of scrambling.
Were there any other impacts people wouldn't have noticed?
Astronauts on the International Space Station had to take shelter during the worst of the storm. The ISS orbits at about 250 miles altitude, which is above most of Earth's protective atmosphere, so astronauts are more exposed to radiation.
What does take shelter mean in space?
The ISS has areas with better shielding, usually the sleeping quarters or modules surrounded by more equipment and water storage. Astronauts move to those areas and avoid spacewalks during radiation storms.
Because a spacewalk during a solar storm is...
A very bad idea. You'd be exposed to significantly elevated radiation levels. Not immediately deadly, but enough to increase cancer risk and potentially cause radiation sickness if the dose was high enough.
That's cheerful.
Space is not a friendly environment, especially during solar maximum. But there's actually a positive side to this storm.
There is?
Debris removal. Remember I mentioned the atmosphere expanding during the storm? That increased drag doesn't just affect active satellites, it also affects space junk. Thousands of defunct satellites and debris objects had their orbits decay faster.
So the storm cleaned up space trash?
To some extent, yes. Debris that would have stayed in orbit for years came down months or years earlier. One researcher called the storm one of the best things for maintaining a long-term operable environment in low Earth orbit.
The silver lining to a solar storm.
Exactly. Those satellite operators probably didn't appreciate having to maneuver thousands of active satellites to avoid collisions with all that descending debris.
Speaking of which, how many close calls do we have?
That's hard to say publicly, but the conjunction assessment infrastructure, the system that tracks potential collisions, was overwhelmed. The storm produced large and unpredictable perturbations in satellite trajectories, making collision predictions unreliable.
That sounds like a recipe for disaster.
It could have been. The fact that we didn't have any major collisions is partly good design and partly good luck.
For now.
For now. But with tens of thousands of new satellites planned for the next few years, storms like this are going to become a much bigger operational challenge.
Okay, I want to go back to something you mentioned. The fact that we had warning. How much advance notice did we have?
NOAA issued the initial watch on May 8th for potential impacts starting May 10th. So roughly 2 days advance warning.
That seems short.
It is, relatively speaking. The challenge is that CMEs travel at variable speeds and can accelerate or decelerate en route. We can see them leave the sun using coronagraph images, but predicting exactly when they'll arrive and how strong they'll be is tricky.
So the forecasts were wrong?
Actually, there's a fascinating study on this. Researchers analyzed the forecast accuracy leading up to the May 2024 storm and found that even 1 day in advance, the magnitude and duration were poorly predicted.
How badly off were they?
The Geomagnetic Activity Index, AP, peaked at 271, making it the second highest ever recorded. But the forecasts, even 24 hours beforehand, were predicting much lower values. The storm ended up being roughly twice as strong as expected.
So even with all our technology and models, we still can't predict space weather accurately.
We're getting better, but yes, there's a lot of uncertainty. It's like hurricane forecasting was 50 years ago. We know the storm is coming and roughly where it'll go, but the intensity is hard to pin down.
That's not particularly reassuring given how dependent we are on technology.
No, it's not, which is why there's such a push to improve space weather forecasting. ESA has a mission called Vigil planned that would give us views of the sun side before it rotates into Earth-facing position.
So we could see the active regions earlier.
Potentially 4 to 5 days earlier, yes. That would be a game changer for preparation.
All right, let's take a break here. When we come back, we need to talk about what people actually saw because those auroras were spectacular. And then we'll get into the scary stuff. What happens if we get hit by something even bigger?
Welcome back. We talked about the technical impacts of the May 2024 solar storm, satellites, power grids, GPS, but for most people, this storm was about one thing, the auroras. Alina, I saw photos from places that should never see the northern lights. What happened?
The May 2024 storm produced aurora at some of the lowest latitudes we've seen in decades. Reports came in from Puerto Rico at 18 degrees north latitude, from Mexico, from the southern United States. In the southern hemisphere, Aurora australis was visible from South Africa, Australia, and South America.
How is that possible? I thought auroras only happen near the poles.
Under normal conditions, yes. Auroras occur where Earth's magnetic field lines funnel charged particles down into the atmosphere, and those field lines naturally converge at the magnetic poles. But during a severe geomagnetic storm, the entire magnetosphere gets compressed and distorted.
Like squeezing a balloon.
Good analogy. When billions of tons of plasma slam into our magnetic field at 3 million miles per hour, the field gets pushed inward on the sun-facing side and stretched out on the night side. This compression allows particles to reach much lower latitudes.
So the aurora oval expands.
Exactly. Under normal conditions, the aurora oval sits around 65-70 degrees latitude. During a G5 storm, it can expand down to 40 degrees or even lower. That means places like New York, Madrid, Rome, cities that rarely see auroras, suddenly have them overhead.
And the colors. I saw photos with intense reds that I've never seen in typical aurora photos.
That's one of the most interesting aspects. The color of an aurora depends on 3 things: altitude, which gas is being excited, and the energy of the incoming particles.
Break that down for me.
Sure. The classic green aurora, the one everyone thinks of, comes from oxygen atoms at about 100-150 kilometers altitude. Oxygen emits green light when excited by relatively low-energy electrons.
And the red?
Red also comes from oxygen, but at much higher altitudes, 200 kilometers and above. Up there, the atmosphere is so thin that oxygen atoms have time to emit red light before colliding with other atoms.
So red means the particles are penetrating higher into the atmosphere?
Or that the energy is high enough to excite oxygen at those altitudes, yes. During severe storms, you get these brilliant red auroras that can extend very far south.
The photos looked almost blood red in some cases.
That's actually similar to what people described during the Carrington Event. Historical accounts talked about blood red skies so bright you could read a newspaper by the light.
Which brings up an interesting point. How do we know the Carrington Event was worse if we didn't have satellites or modern instruments?
Great question. We rely on proxy measurements. The main one is magnetometer data, measurements of Earth's magnetic field from ground stations. Several observatories in 1859 had magnetometers recording when the storm hit.
And what did they show?
The disturbance in Earth's magnetic field, measured by the DST index, dropped to somewhere between -800 and -1750 nanoteslas, depending on whose analysis you trust.
So Carrington was roughly twice as strong, maybe more?
At least twice, possibly 4 times stronger at its peak. And the effects were more dramatic because the storm was so fast. The CME traveled from sun to Earth in only 17.6 hours.
Why does speed matter?
Faster CMEs carry more kinetic energy and tend to have stronger shock waves. They also compress the solar wind ahead of them, which can enhance the magnetic field strength.
So the Carrington CME was basically a freight train compared to May 2024's sports car.
More like May 2024 was a sports car and Carrington was a bullet train. But yes, speed matters.
Okay, back to the auroras. I want to know, what did people actually see? Because I imagine it varied a lot by location.
Hugely varied. At high latitudes, Alaska, Canada, Scandinavia, people saw the full aurora experience. Dancing curtains of light, coronas directly overhead, rapid movement and color changes.
The classic aurora.
Right. But at mid-latitudes, say 40 to 50 degrees, people saw something different. Often a bright glow on the northern horizon that would flare up periodically in red or purple.
Not the dancing curtains?
Not occasionally, but more often a diffuse glow with occasional structured features, and the colors tended toward red rather than green because you're seeing the higher altitude emissions.
What about the really low latitudes, like Puerto Rico?
At 18 degrees north, people probably saw a faint red glow on the northern horizon during the peak of the storm. You'd need really dark skies and clear weather to see it, but it was there.
And social media went crazy.
Oh yes, Aurora was trending worldwide. People who'd never seen the northern lights in their lives were posting photos from their backyards.
Were all the photos real, or was there camera trickery involved?
That's an important question. Modern smartphone cameras are actually very good at capturing auroras because they can do long exposures and boost sensitivity.
So the photos showed more than the naked eye could see.
Often, yes. A camera with a 10-second exposure will gather more light than your eye can in real time. So a faint glow that looks whitish or barely visible to your eye can show up as vivid green or red in a photo.
So some people were photographing auroras they couldn't actually see.
In some cases, yes. But that doesn't mean it wasn't real. The camera was just more sensitive than human vision. And at the peak of the storm, many people could see the aurora with the naked eye, even at mid-latitudes.
How long did the display last?
That's what made this event special. We had auroras below 50 degrees latitude for roughly 42 hours, nearly 2 full nights. Most geomagnetic storms last hours or maybe a day. This one just kept going.
Because multiple CMEs kept hitting us?
Exactly. It wasn't one impact. It was a series of impacts over several days. Each CME would arrive, create a new burst of auroral activity, and then the next one would hit before conditions fully calmed down.
A 1, 2, 3 punch from the sun.
More like a 1, 2, 3, 4, 5, 6, 7 punch. AR3664 was incredibly active.
Speaking of AR3664, what happened to that sunspot region? Did it just disappear?
This is where it gets really interesting. After causing all this chaos, AR3664 rotated around to the far side of the sun, out of Earth's view around May 14th. And on its way out, it fired off one last parting shot.
Of course it did.
An X 8.7 class solar flare, the strongest of the entire solar cycle at that point. Fortunately, it was aimed away from Earth.
Thank God for some small favors.
But wait, there's more. AR3664 survived its trip around the sun's far side and came back into view 2 weeks later.
The sunspot region came back?
Sunspot regions can persist for weeks or even months as they rotate with the sun. AR3664 returned in late May, now designated AR3697, after merging with another active region, and it was still firing off powerful flares.
So we had to deal with it twice?
We're still dealing with it, actually. The region continued to be active through June, firing multiple X-class flares. It became the gift that keeps on giving or the nightmare that won't end, depending on your perspective.
Why was this particular region so active?
The magnetic field configuration. Sunspot regions form where intense magnetic fields poke through the sun's surface. When those fields are highly twisted and complex, like AR3664 was, they store enormous amounts of magnetic energy.
And when that energy releases,
you get solar flares and CMEs. The more twisted and sheared the magnetic field, the more powerful the eruptions can be.
is there any way to predict which sunspot regions will be hyperactive like this?
We're getting better at it. Solar physicists look at the magnetic field topology, the complexity of the sunspot structure, how fast it's evolving, but it's still not an exact science.
So we could wake up tomorrow and find another AR3664-like region?
Absolutely. In fact, we should expect more as we approach solar maximum.
Which is...
predicted to occur between late 2024 and early 2026. We're right in the peak period now.
So what you're saying is, May 2024 might be a preview of what's coming.
That's exactly what I'm saying. The sun operates on an approximately 11-year cycle of activity. Right now, we're climbing toward the peak. More sunspots, more flares, more CMEs.
More opportunities for disaster.
Or more opportunities for spectacular auroras, depending on how you look at it.
I feel like you're trying to put a positive spin on this.
I'm a glass half full kind of astrophysicist. But seriously, we need to talk about the real risks because May 2024 was relatively gentle compared to what could happen.
And that's where we're going after the break, the nightmare scenarios. What if the next storm isn't G5, but something even worse? All right, we're back, and it's time for the part of the show where Elena scares the hell out of me by explaining what happens if we get hit by a Carrington-level event in our modern technological society.
I prefer to call it motivating preparation through informed concern.
That's a very diplomatic way of saying this could be really bad.
Okay, let's do this. So, first thing to understand, the Carrington Event of September 1st, 1859 remains the largest geomagnetic storm in recorded history.
We touched on this earlier, but give me the full story.
On September 1st, 1859, British astronomer Richard Carrington was observing sunspots through his telescope, with proper eye protection, of course, when he saw a bright flash of white light erupt from the sun's surface. This was the first observed solar flare.
And he realized it was connected to what happened next?
He suspected a connection, though he was cautious about claiming it definitively. About 17.6 hours later, the fastest CME ever recorded slammed into Earth's magnetosphere.
17 hours? That's terrifyingly fast.
It's believed a previous CME had cleared the way by pushing aside the normal solar wind,
allowing the main CME to travel through essentially empty space.
So it had a clear runway.
Exactly. And when it hit, the results were spectacular and terrifying. Auroras were visible globally, from the Caribbean to Australia. People in the Rocky Mountains were woken by the brightness, thinking it was dawn. Gold miners started making breakfast at 2 a.m.
That's absurdly bright for an aurora.
Historical accounts say people in the northeastern United States could read newspapers by the aurora's light. The sky was literally bright enough to cast shadows.
And the technology impacts?
The telegraph systems worldwide went haywire. Telegraph operators reported receiving electric shocks, sparks showering from equipment, and paper in telegraph offices catching fire from the electrical surges.
Fire from a solar storm?
Yes, the geomagnetically induced currents in the telegraph wires were powerful enough to arc and ignite paper. One operator in Washington, D.C. said he saw a spark jump from his forehead after being shocked.
That's horrifying.
What's remarkable is that some telegraph lines could actually operate without batteries during the peak of the storm. The induced currents were strong enough to power the system.
Nature provided the electricity.
Temporarily, yes, but it also destroyed a lot of equipment. Now here's the critical question. What would happen if the Carrington level event hit Earth today?
Do I want to know?
You probably should know. In 2008, the National Academy of Sciences commissioned a study on this exact scenario. Their conclusion? A Carrington-level event today could cause between $1 and $2 trillion in damage.
That's more than most countries' GDPs.
It would be the most expensive natural disaster in human history. And here's the scary part. The recovery time could be years, not weeks or months.
Why so long?
Because of those high-voltage transformers we talked about earlier. They're custom-built, expensive, and take 12 to 18 months to manufacture and install. If hundreds or thousands of them fail simultaneously, you can't just order replacements off a shelf.
So parts of the power grid could be down for years.
In a worst-case scenario, yes. And without power, everything else cascades. No pumps for water systems, no refrigeration for food, no fuel pumps for gas stations, limited communications.
That sounds like a collapse of modern civilization.
It wouldn't be quite that apocalyptic, but it would be the largest infrastructure disaster we've ever faced. Some researchers have estimated it could reduce agricultural yields by 38 to 48% globally due to disrupted supply chains.
Because farms can't get fertilizer, pesticides, irrigation?
Exactly. The indirect effects cascade through every system that depends on electricity and communications, which is basically everything.
Okay, but this is all assuming a direct hit from a Carrington-level CME. What are the odds of that actually happening?
Scientists estimate about 12% chance in the next 100 years. Some studies suggest we experience a Carrington-level storm about once every 500 years.
So rare, but not impossible.
And here's something to keep you up at night. We narrowly missed one in July 2012.
Excuse me?
On July 23rd, 2012, the sun fired off a Carrington-class CME. Massive, fast, powerful, but it was aimed at a part of space where Earth had been about 9 days earlier.
So if Earth's orbit had been slightly different,
we would have taken a direct hit. The Stereo A spacecraft, which happened to be in the path, measured the CME and found it comparable to the Carrington event in size and speed.
That's absolutely terrifying.
It's a reminder that these events aren't just historical curiosities. They happen. The question is when, not if, the next big one hits Earth.
So what are we doing to prepare? Are we building better shielding, backup systems, hardened infrastructure?
Yes and no. Some utilities have taken steps: better surge protection, more robust transformers, protocols for shutting down vulnerable equipment when a storm is incoming.
but it's expensive and not universally implemented.
So we're partially prepared.
We're more prepared than we were in 1989, but not as prepared as we should be given the risks. The challenge is that infrastructure upgrades cost billions of dollars to protect against an event that might not happen in our lifetimes.
The classic risk management problem.
Exactly. Do you spend billions now to prevent a potential trillion-dollar disaster later? Economically, it makes sense, but politically, it's a hard sell.
What about satellites? Can we build them to survive these storms?
To some extent. Modern satellites have better radiation shielding, redundant systems, and the ability to enter safe modes. But there are limits. A truly severe storm would still cause losses.
How many satellites might we lose in a Carrington-level event?
That's hard to estimate, but one simulation suggested we could lose all our satellites in a worst-case scenario. That's probably hyperbolic, but we could certainly lose many of them, especially in low Earth orbit.
And once they're gone, replacing them takes years.
Years and billions of dollars. GPS would be degraded or non-functional. Communication satellites would be down. Earth observation satellites for weather and climate monitoring would be gone. It would be a massive setback.
Okay, you've successfully terrified me. Is there any good news?
Actually, yes. Solar weather forecasting is improving dramatically. We now have multiple spacecraft watching the sun from different angles.
Like having security cameras pointed at the sun.
Exactly. NASA's Solar Dynamics Observatory watches in multiple wavelengths. The SOHO spacecraft has been providing coronagraph images for decades. ESA's Solar Orbiter can see the sun's poles and far side.
So we'd have warning.
Typically 15 to 18 hours for the fastest CMEs, a few days for slower ones. That's enough time to put satellites in safe mode, alert power grid operators, ground flights if necessary.
But not enough time to evacuate cities or anything dramatic.
No, because we don't need to. People on the ground are safe. Earth's atmosphere and magnetic field protect us from the radiation. The danger is to technology, not to humans directly.
Unless you're an astronaut on the ISS.
Or on a flight at high altitude. Airlines do reroute flights away from polar regions during radiation storms to reduce exposure for crew and passengers.
Is the radiation actually dangerous?
It increases exposure, but flying through a solar radiation storm is comparable to getting a few chest x-rays. Not acutely dangerous, but not something you want to do repeatedly.
What about people claiming solar storms affect human health or behavior?
Oh, here we go. No. There's no scientific evidence that geomagnetic storms directly affect human health or behavior. Some people claim they get headaches or mood changes, but controlled studies haven't found any correlation.
So it's all in their heads.
Or it's coincidence, or it's the power of suggestion. The only proven effects are technological.
Okay, final question about the nightmare scenario. What's the absolute worst case beyond Carrington?
You want to know about super flares.
I'm not sure I do, but yes?
Super flares are hypothetical solar eruptions that could release up to 1,000 times more energy than the Carrington event.
1,000 times more?
We've observed super flares on other sun-like stars that rare, maybe once every few thousand years, but they're possible.
And if one hit Earth?
That would be an existential threat. We'd be looking at complete destruction of the power grid, loss of all satellites, potential damage to electronics even if they're turned off. It would be civilization altering.
But that's extremely unlikely.
Extremely unlikely, yes. But extremely unlikely isn't the same as impossible. The sun is capable of surprises.
You are really good at the whole informed concern thing.
I try, but look, the important takeaway is that we can prepare for these events. Better forecasting, hardened infrastructure, clear protocols. We're not helpless.
Just partially vulnerable.
Partially vulnerable, yes, but awareness is the first step toward resilience.
All right, I want to talk about where we go from here, what the May 2024 storm taught us, and what's coming as we head toward solar maximum.
Welcome to the final segment. We spent the last minutes talking about the May 2024 solar storm, the science behind it, and the potential for even worse events. Elena, let's wrap up by talking about what we learned and where we go from here.
Sure. I think the May 2024 storm was a wake-up call. It showed us that even though we've made progress in space weather forecasting and infrastructure resilience, we still have vulnerabilities.
What were the biggest surprises?
For me, it was how much the satellite operators struggled with trajectory prediction. When you have half the satellites in low Earth orbit maneuvering simultaneously because of atmospheric drag, that creates collision risks we hadn't fully appreciated.
Because everyone's dodging at once.
Right, and the automated collision avoidance systems weren't designed for that scenario. It worked out, but it exposed a weakness in our space traffic management.
What about the power grid?
The good news is the grid held. The improvements made since 1989 paid off. But NOAA's report mentioned power grid irregularities, which suggests we were closer to problems than the public realizes.
So we dodged a bullet, but it was close?
I'd say we took a glancing hit rather than a direct impact. If the magnetic field conditions had been slightly more favorable for coupling with Earth's field, or if AR3664 had fired one more massive CME our direction, we could have seen localized blackouts.
And that would have caused panic.
It would have been a major news story, yes. Solar storm causes power outages across multiple states would have been quite the headline.
But we avoided that. So in some ways, May 2024 was the best case scenario for a G5 storm?
In terms of impacts, yes. We got the spectacle without the catastrophe. Though I'm sure satellite operators and power grid engineers would describe it differently.
They'd probably say it was stressful as hell.
Without question. But it was also a valuable learning experience. We now have real data on how modern satellite constellations behave during severe storms, how forecasting models perform, where our vulnerabilities are.
So what changes are being made?
There's a renewed push for better space weather forecasting, especially getting multiple viewpoints of the sun. ESA's Vigil mission, which we mentioned earlier, would provide crucial early warning.
By seeing the sun's side before it rotates into view?
Right. Currently, we can only see the Earth-facing side. If a dangerous active region is on the far side, we don't know about it until it rotates into view, and by then we have maybe a week or less to prepare.
How much would Vigil help?
It would give us 4 to 5 extra days of warning. That could be the difference between orderly preparation and scrambling to respond.
When does it launch?
It's still in development with a launch possibly in the late 2020s. These missions take time to design, build, and fund.
What about improving forecasting models themselves?
That's an active area of research. The May 2024 storm showed that even 24 hours in advance, we were off by a factor of 2 on the storm's intensity. We need better models of how CMEs propagate, how they interact with each other, how the magnetic field evolves.
And is artificial intelligence helping with this?
Actually, yes. Machine learning models are being trained on decades of solar observations to identify patterns that humans might miss. There's an IBM-NASA collaboration working on AI that can predict solar flares.
Can it actually predict them?
With some success, yes. It's not perfect, but it's an improvement over previous methods. The challenge is that solar flares and CMEs are chaotic phenomena. Small differences in initial conditions can lead to very different outcomes.
The butterfly effect in space weather.
Exactly. But the more data we have and the better our models become, the more accurate our forecasts will be.
Okay, let's talk about the near future. We're heading towards solar maximum. What should people expect?
More sunspots, more flares, more CMEs. We're likely to see more auroras at mid-latitudes over the next year or two. And there's a decent chance we'll see another G4 or G5 level storm.
How likely?
Hard to put a number on it, but I'd say maybe 20 to 30% chance of another severe storm before the solar maximum passes. The sun is unpredictable.
Should people be preparing for blackouts or anything?
The same basic emergency preparedness that applies to any natural disaster. Have water, food, batteries, a way to get information if the power's out. But I don't think we need to be building bunkers or anything.
That's reassuring, I guess.
The key thing to remember is that severe space weather events are more likely to cause disruptions and inconveniences than true disasters. Your power might flicker, your GPS might be wonky, your satellite internet might be slow. Annoying, but manageable.
Unless we get hit by that Carrington-level event.
Even then, it's about infrastructure resilience, not human survival. We're not talking about an asteroid impact or a nearby supernova. We're talking about damage to technology that we can eventually repair.
On the scale of months to years?
In a worst case, yes. But most likely we'd see a mix of outages and service degradations that get fixed over weeks.
Okay, rapid-fire question round for the ending. Ready?
Hit me.
Will we see AR3664 again?
Possibly. Sunspot regions can persist for multiple rotations. It came back once already as AR3697, so maybe it'll survive for a third or fourth pass.
What's the biggest misconception people have about solar storms?
That they're directly dangerous to humans. Unless you're in space or on a high-altitude flight, you're safe. The danger is to technology.
Could a solar storm knock out the entire internet?
Unlikely. Most internet infrastructure is underground or well shielded. You might lose satellite internet and have disruptions to long-distance fiber connections, but the core internet would survive.
Would solar panels on houses survive a Carrington event?
If they're connected to the grid, they could be damaged by the induced currents. If they're disconnected or have proper surge protection, they'd probably be fine.
Could solar storms trigger earthquakes or volcanic eruptions?
No, there's no physical mechanism for that. Some people claim correlations, but rigorous studies find nothing.
Fair. What's the coolest thing about the May 2024 storm that we haven't talked about?
Ooh, good question. The Solar Orbiter spacecraft, which is studying the sun from unusual angles, captured an X-12 class flare from AR3664 that occurred on the sun's far side. This was the strongest flare of the entire solar cycle at that point, and we only know about it because of Solar Orbiter's unique position.
So AR3664 was firing off even more powerful flares that we didn't get hit by.
Exactly. We saw its Earth-directed flares, but it was launching even bigger eruptions in other directions. It was truly a hyperactive region.
That's simultaneously cool and terrifying.
Space weather in a nutshell.
All right, final question. What should listeners take away from this whole story?
I think the May 2024 storm showed us that space weather is real. It's unpredictable, and it affects our technology-dependent society more than most people realize. But it also showed us that with good forecasting, preparation, and resilience, we can handle these events.
Even if we can't prevent them?
We'll never prevent them. The sun is going to do what the sun does. But we can be ready for them. And honestly, I think there's something humbling and beautiful about seeing those auroras and remembering that we live on a planet connected to a dynamic, powerful star.
The cosmos reminding us we're not in control.
Exactly. We're passengers on a rock orbiting a nuclear furnace that occasionally burps in our direction. And when it does, we get these spectacular light shows that have amazed humans for millennia.
I like ending on that note. Elena, thank you for walking us through this. This has been fascinating and only moderately terrifying.
I call that a success. Thanks for having me, Marcus.
For everyone listening, if you want to track space weather yourself, check out NOAA's Space Weather Prediction Center at spaceweather.gov. They have real-time data, forecasts, and alerts. And if you're lucky enough to be at mid or high latitudes, keep an eye on the Aurora forecasts. We're in prime viewing years.
And if you see those auroras, take a moment to appreciate that you're watching the sun and Earth interacting in real time. It's physics made visible.
Poetry from an astrophysicist.
I have my moments.
All right, everyone, this has been Solar Storm AR3664, the 3 million mile per hour blast that painted Earth in fire. I'm Marcus Chen.
And I'm Dr. Elena Vasquez. Thanks for listening, and remember, look up, but maybe wear sunscreen.
And solar eclipse glasses if you're staring at the sun.
Yes, please don't stare at the sun without protection.
Safety first, even in astrophysics. Until next time, stay curious and stay safe.